Everyone to the Wednesday session. So it's 9 o'clock sharp. So today we're very happy to have Francis Brown here. He will talk about, let's see, canonical Feynman integrals and cohomology of GLN. Perfect. Go ahead.
Thank you for the invitation, first of all, and thank you for reminding me of my title, which has slipped my mind. So this conference is primarily about physics. So let me actually talk about a slightly different part of, different corner of physics than the one that's been covered mainly in talks up to now. And that's Feynman amplitudes. So a quick bit of motivation. We start with a Feynman graph, G. And it's a finite connected graph. Looks a bit like this. I'm not going to define it formally because it would just take too long. So we have a finite connected graph. It's also allowed a certain number of external half edges, which we think of as incoming particles. And these particles have momenta. So here there are 4 of them. And the momenta will be taken in Euclidean space of dimension d. And in my talk, d will be equal to 2 or 4. Oh, and momenta subject to momentum conservation, which is the total sum of incoming momenta, is 0. In addition, a Feynman graph comes with data of a particle mass, ME, which is a non-negative real number. It's allowed to be 0. So this is for each internal edge. And what is done in this field is to associate to such a graph of what's called a Feynman integral, which is a function of the particle momenta and the masses. And one of the big headaches in the subject for a long time is that this normally diverges. And it's just infinite or ill-defined or something like this. So what I want to talk about in this talk is something I call canonical Feynman integrals. And I will show that they are related in a very natural way to stable cohomology of general linear groups in various fields, the reals, complex numbers, and the quaternions. And this also is close to one of the other themes of the conference, which is modular forms. These canonical Feynman integrals are always finite. They always converge. And they have a lot of very special properties. Now, it turns out, so to sort of give away a teaser, is that they will turn out to be certain volumes on moduli spaces of tropical curves. So here we link with this amplitude-hedron program of Nima Arkhani-Hamed and his collaborators, seeking to interpret certain amplitudes and n equals 4 Yang-Mills as volumes on certain types of Grassmannians. And we also connect with string perturbation theory, which is a popular topic in this conference, where we're integrating on moduli spaces of actual curves. Here we're going to integrate on moduli spaces of tropical curves, and they're going to give something very close to classical Feynman integrals. So I'd like to explain that, but first some history or motivation, which is one of the early connections between number theory and physics, at least it was for me. So for the time being, I'm just going to take vacuum diagrams as a simplification. So these are graphs with no external legs, and all masses are zero. So an example of a vacuum diagram is this. And it might not look very physical, but it has its uses, don't worry. Okay, so going back to Kirchhoff in the 19th century, you can associate to this a polynomial with integer coefficients in certain variables called Schwinger parameters, which are indexed by every edge in the graph. It is homogeneous. And was first defined by Kirchhoff in his study of electrical circuits in the 1850s, I think. The definition is that you take the sum over all spanning trees, and for every spanning tree, you take the product of all Schwinger parameters not in that tree. So in this case, so I should quickly do it, the spanning trees, if I number the edges 1, 2, 3, the spanning trees are 1, 2, and 3. They're certainly trees, and they span, meaning that they meet every vertex. So spanning means that VT equals VG. That's what the meaning of span is. And so you take the complement of each of these sets and multiply by all the alpha parameters. Here you get alpha 2, alpha 3, plus alpha 1, alpha 3, plus alpha 1, alpha 2. So it's a very interesting polynomial. And what's called the residue, which is the residue in epsilon in dimensional regularization, if you know what that means. But it's a very simplified version of a Feynman integral. And you integrate in projective space over the region where the alphas are positive of a certain projective differential form of a psi g squared, where omega g is the sum over all the edges, ordered in some way, it doesn't matter. And here you omit the ith variable. And here I note G is the number of edges in my graph. Right, so these things were studied by Broadhurst and Kramer in the 90s. And were an inspiration to many of us to begin to get interested in this subject. The first such example is very classical. I don't know who the first person to compute this was, but the simplest example of such a graph. So I should say that this is not always finite. This residue it's not always, it can be infinite, can diverge, but we know precisely when it's finite. And I won't give the conditions, it's not very relevant for me today, but the graphs I'm going to write down here satisfy that condition. And so the integral here is 6 is each of 3. Here's the wheel with 4 spokes. Many of you would have heard me give many talks on this many years ago. I used to give lots of talks on this, but I haven't done so for a long time. 20 is each of 5. In general, the n+1th wheel, so n denotes the number of spokes, sorry, n+1 denotes the number of spokes, is a Catalan number times zeta 2n-1. Okay, and more interestingly, the graph K34, which is a complete bipartite graph, which is extremely difficult to compute. Oops. I think that's right. 1, 2. Yes, that's correct. Looks a bit funny. Gives a certain multiple, a rational multiple times zeta 3, zeta 5, plus a rational multiple of a multiple zeta, zeta 3 comma 5, minus 29 over 12 zeta of 8. And this is a genuine multiple zeta and is the start of a lot of research into trying to understand why Feynman integrals give multiple zeta values. Now, I'd like to draw your attention to this particular, it's only ever this particular linear combination which occurs. This 29 over 12 is important and will come back again later. Now, a quick comment is that this is a highly simplified or stripped down version of a quantum field theory. In general, and remaining in the context of vacuum diagrams, we'd get much more complicated integrals. We would, in say, quantum electrodynamics or well, a more general quantum field theory than this very simplified version, we would expect to get integrals with higher powers of the Kirchhoff polynomial in the denominator and some typically very complicated numerator, which is a polynomial in the alpha e's. And the canonical integrals that I will first of all consider will be of this form. All right, so the first step is the question is what is, so despite this huge amount of work understanding the mathematics of Feynman integrals, the question remains, which is what is the mathematical meaning of a Feynman integral, to which I don't know the answer. But we can try to bring it closer to sort of mainstream questions in pure mathematics in stages. So the first thing to do is to try to interpret this polynomial psi g. And this is very well known, and it involves the graph Laplacian. So to a graph G, again, for now on, I'm just in the case of vacuum diagrams for most of the talk. I will return to kinematic case at the end. So to G, we associate a matrix called the graph Laplacian matrix, which is a Hg by Hg symmetric matrix, where Hg is the loop number. If you like, it's the rank of H1 G of Z, which is a free Z module. Okay, so how do we compute the graph Laplacian? There are highbrow definitions. I'm going to give a very down-to-earth one, which will depend on choices. So if we first choose an orientation on the edges, then we choose a basis of cycles. So C1, so these are homology cycles, CHG, and they are linear combinations of edges. And then we form the incidence matrix, I call HG, and it is an EG. So there are lots of incidence matrices of different descriptions between vertices and edges, vertices and loops, loops and edges. This is one of the many different possibilities. And its entry, EI is the coefficient of edge E in the cycle Ci. And finally, we set DG to be the diagonal matrix with all the Schwinger parameters sitting on the diagonal. And the graph Laplacian matrix, or a graph Laplacian matrix, is HG transpose DG, HG. So an example. So I'll do the same example as here. We have the sunrise diagram. Oops, with 3 edges. And let's orient. So first step is to orient the edges. I'll do it like this. So this is 1, edge 2, and edge 3. A basis for cycles, so we could add some colors. C1 would be this cycle. What should I do? And then C2 will be this cycle. So C1, maybe not so visible. C1 is E1 minus E2, and C2, sorry, E1 plus E2. Go along E1 and then along E2 in the positive direction, and C2 is E2 plus E3. So I've arranged it so that the signs are positive. This matrix HG, its rows are indexed by the cycle C1, C2, and its columns by the edges. Let me simply read off this information. 0, 1, 1. And when you plug in this formula here, we get that the graph Laplacian with respect to these choices is exactly alpha 1 plus alpha 2, which is really just this cycle. And alpha 2 plus alpha 3, and alpha 2 and alpha 2. Sure, yeah, shall I raise that? So I'll continue here. So you can check, you can convince yourself that the determinant of this matrix is precisely the graph polynomial psi g. In this case, it's exactly this polynomial up here. So this is a theorem, a very well-known theorem. And it's sort of equivalent to what's called the matrix tree theorem. So it's very well known. I'm not sure who the first person to state it was, but it's been known for a long time. And now, so the interesting remark here is that, so of course, this Laplacian is not well defined. One can make it intrinsic, but as a matrix, it's not well defined. And in fact, if you were to change bases, so if you were to change, was the question? Why do you have to base it otherwise? You just map from cycles to the cycles. Absolutely, absolutely. As a map from the cycles to cycles, it's well defined. And as you know, the determinant is well defined because it's intrinsic. Essentially, because the determinant of an integer matrix, an invertible integer matrix, is plus or minus 1, and we're going to get minus 1 squared. Let me just say that this will be an important point for motivating what I'm going to do next. I want to write down the effect of the changing basis on this matrix. So if I were to change change basis, what it would do is transform this matrix into P transpose lambda GP. So this is important, where P is an element of GL HGZ. So, and as I just said, that so the point is that the determinant could be plus or minus 1, but the determinant is well defined because you're going to get minus 1 times minus 1. But that's not the only way to get, the determinant is not the only way to get something well defined out of a square matrix. There's something called the invariant differential. And that's what I want to talk about. So, So for any graph G, I'm going to define omega ng is something a bit more sophisticated than the determinant. It's the trace of the inverse of the graph Laplacian d lambda g raised to the nth power. Now, the first remark is that this is always well defined. And that's because if you multiply, well, it's obvious that if you multiply lambda g on the left by something in GLHGZ, then clearly, lambda g inverse d lambda g doesn't change, so the whole thing doesn't change. It's slightly less obvious that if you multiply on the right, it's invariant, but that involves the properties, the cyclicity properties of the trace. It's a very easy exercise. So it turns out that this is completely well defined. And that means, in fact, that if you define a switch notation, if you take any matrix X whose entries are in some differential graded algebra, for example, and you take X inverse dx to the n, then this is bi-invariant. For all A, B, in fact, in GLHR, more generally. Secondly, these forms are always closed. So D of omega nx is 0 always. They're well defined. Oh, yes. And they vanish in a lot of cases. They vanish when n is even. But they additionally vanish if n is congruent to 3 modulo 4. If the matrix is symmetric, which it is. So this is because lambda g is symmetric. And again, this just uses very basic properties of the trace. So we can look at these forms for general matrices. If the matrix is not symmetric, then you do indeed get some other interesting differential forms congruent to 3 mod 4. But for now, we're only going to. Yep. Did I write? Oh yeah, thank you. Well, actually, it's true that it's true for beta, but let's just write omega g. Thank you. Good. So then what we can do is take, so these are nice differential forms in the alphas. So they're, if you like, polynomials in, they're polynomials in the alphas, the d alphas, and 1 over the determinant of lambda g. So clearly, when we invert this matrix, we're going to have to divide by the determinant, and the determinant is the graph polynomial. So we're going to get something looking mighty like a Feynman differential form, Feynman integrand. I'm going to be slightly sloppy with notation, but I call the canonical algebra omega can is the graded exterior algebra on these guys. So I'll just view them as, they'll just be formal symbols. First one is omega 5, omega 9, omega 13, and there's for every integer congruent to 1 modulo 4, there is a recipe, and we can apply it to any graph we like. Now you may wonder why I've omitted omega 1. Omega 1 is badly behaved, and so I discard it. Right, so we have a graded exterior algebra on certain symbols, if you like, and these symbols can then be evaluated on any graph, and they give differential forms. So here comes the definition then. Define for G any graph, again a vacuum, we're still in the world of vacuum diagrams, no external legs. And if I take any form in this canonical algebra, So it could be an exterior product, you know, it could be something like omega 5 or omega 9, that's fine. But it needs to be homogeneous of degree equal to the number of edges minus 1. Then I can define a canonical integral associated to my graph, which is, and I run out of chalk, which is the integral, again, over the region where the Schrödinger parameters are positive of this completely canonical form. So that's the first instance of a canonical Feynman integral. So the theorem, in a paper I published in 2021, I'm afraid I don't have the archive reference to hand. It's very easy to find. There are lots and lots of properties of these. I'll just give one or two. The most important one is that this integral is always finite. So it always converges, which is by contrast with the residues we considered earlier.
You motivate the omega G by saying that the term is invariant, but it's not the invariant thing.
Yes.
What's the relation with the term that the psi G to omega G is invariant?
Psi G, let me just actually, I'll just say that in a second. So yes, we'll use that fact now, presently, because omega G, well, by definition, if d lambda G, so you have a matrix. This is a matrix whose entries are involves d alphas, right? So maybe this often causes confusion. So perhaps I should just say what I mean. That should become clear. So to make this form, we should work in a DGA or something, but it's not important. So d lambda G is literally the matrix with you know, when you differentiate term by term. G alpha 2 is D alpha 3. So then you're going to compute the inverse of this matrix, and that's going to produce 1 over the determinant. So expect to find the determinant to some power, and then we're going to get some polynomial in the alphas. And then when we multiply these matrices together, we're going to get wedge products of all these alphas. And because of the degrees, we're going to get omega G. There's something to prove there, but so NG is some polynomial in the alphas. In fact, it has integer coefficients. So a priori, this K is related to the omega G is any omega canonical differential form. It's just omega, but it depends on when I plug in the Laplacian of a given graph, it's going to change completely. Yes. Omega G without an N. Here, so omega can is the graded exterior algebra on symbols. I said this, I didn't explain it. On certain symbols called omega. So I pick an omega in this algebra, and then omega sub G means
Oh, I see. It's not the same omega.
It's not the same omega. So these are sort of yeah. It's unfortunate notation, but my notation is that if I have omega with a superscript, the superscript means this particular one in this particular degree, and when it has no superscript, it means it could be an arbitrary polynomial in such. So if I were to write omega with a superscript 5 here, it would mean omega 5G, where it would be exactly this definition. If I were to write omega 5 wedge omega 9, then you know what I know. So the forms are universal, but the integral is all different because the graphs are changing. Right, and so this means that the second point means that they are precisely canonical integrals. Yes. It doesn't really matter. We can take Q, but you can let's just say over Q. It makes sense to do it over the integers, but let's take Q. So canonical integrals are types of Feynman integrals, which always converge, and they have lots of other properties. I don't want to necessarily go into in too much detail today. So I will give you some examples in just a second, but to keep you in suspense, I will first give a geometric interpretation of these canonical integrals, and then I will tell you, give you some examples, and we can compare with the residues. So, need some space. Let me go up here. So how do we think about these? Again, there's a lot to say, so I'm going to be rather brief. Geometric interpretation. So the point is that these integrals have a very clear meaning mathematically. So let PG be the space of positive, definite, symmetric matrices with real entries. So G by G, I forgot to say. G by G, symmetric matrices with real entries. Right, so that's one of the players. And on it, we have GLGZ acts via the formula I wrote down earlier. So if we have P, then X, so let's call them X, X maps to P transpose XP. So we have a very well-studied symmetric space. Now, on the other hand, we have a moduli space of tropical curves. I don't want to define the whole thing. I just want to define a piece of it. So I've taken some shortcuts. I'm going to define, so we have MG trop, the moduli space of tropical curves, genus G. And inside it is a certain open, which is the one of so MG trop involves weighted graphs, so graphs where the vertices have weights. That the meaning of this is it sort of remembers the fact that it's a curve of genus, the weight. Inside that, you have an open locus where there are no weights at all, the weights are zero. And I'm just going to define this, okay? Sorry? No, it's a weight on the vertices. So it represents a stratum in so that it's kind of dual to strata in MG bar, the Deligne-Mumford compactification, and I really didn't want to talk about this, but a vertex with a number on it represents a curve of genus G. Anyway, but I'm going to talk about this thing to save time, and this thing could be described directly as the moduli space of metric graphs with G loops, with HG equals G. And a metric graph is one in which each edge has a length. And often you take this length to be positive or zero, but to save time, I'm going to make this length be a strictly positive real number. And that's going to be okay. So, yeah, let me erase this. So this is a certain space. I've got two spaces. I've got the space of symmetric matrices, it's very classical, and I've got this moduli space of graphs, which is slightly less classical. And so MG trop in shorthand, it's basically obtained by gluing certain cells together. So what we do is for every graph with the fixed number of a specified number of loops, there's some condition on it being stable and so on. I don't want to go into that since it's the detail. And we just take the positive reals to the number of edges. And this is the space of all possible lengths of edges in the graph. And these cells are somehow glued together via some relation. And so this relation, again, very slightly sloppy, but it does actually make sense. This relation is induced by automorphisms of graphs. Really, I should say isomorphisms of graphs, and contractions of edges. So edges which are not self-edges, which are not tadpoles. So when you do the full moduli space, you do things properly, you take a non-strict equality here, and you don't have this condition. But since I'm only interested in the open locus, we're going to do things slightly differently. And to illustrate this, let me draw a quick picture, see what it looks like. So if we take, let's say, well, that's not good color. If we take this graph here, has two edges. So the space, each edge is allowed a length. So that defines the region, the open region in R squared, where, and each point in this region specifies a length of each edge. Now, the first contraction of edges means that on the boundary, when, so this is the space, you know, L1, L2, L1, L2 in R2. This is good, this, but the blue one's terrible. Yellow. Oh, it's going to look the same. The green background. Red. And then, so, but we can also look at the boundary. So this has a boundary clearly where you take the closed quadrant, and we glue in along the axis where L1 equals 0. We view that as being the cell where the length of this edge literally goes to 0, in which case it's this graph here, 2. So this is the cell here in red, oops, associated to this graph. So L2 is, and similarly, we have the same thing when the other edge goes to 0. So this is L1 in R positive. And the key point is that this corner is not in the space. And that's precisely because I've taken this open W equals not 0. So the corner, so when you in the full moduli space tropical curves, what you would represent this by the graph where you contract this loop, and clearly a problem happens because it doesn't have the same number of loops. And so to answer the earlier question, in the full moduli space tropical curves, this point is represented by the graph with just a single vertex with a weight 1, where the 1 remembers the fact that there's a contracted tadpole, right? So that's what happens in the full moduli space. I didn't want to talk about that, but for this talk, we only care about this open locus. And so in this talk, this point here, this corner, is not in the space. No, I took the union. So I've got this cell union. I've got the union over all the graphs. So this is indeed a graph of genus with one loop. No, but it's slightly sloppy because I'm gluing the spaces along along a locus which is outside the space, but it doesn't matter. It makes sense. It's just, as I said, there are various ways to define this space. Some of them are very efficient, but I didn't want to get too bogged down. Technicalities, yes. Oh, thank you very much. Yeah. Thank you very much. And the second thing is automorphisms. Thank you, Eric. Goodness. So, yeah, so this graph has a symmetry which interchanges edges 1 and 2, and that is the involution L1, L2 is equivalent to L2, L1. So it's a reflection along this diagonal. And so in the quotient, this particular part of the moduli space, I'll stick with green, looks a bit like this. It's got a sort of half line, nothing in the end, and then a solid line, a sort of half interval here. So this is a copy of R positive. This is sort of R2 positive mod Z mod 2Z. And there's nothing in the corner. And so that's what mg trop W equals 0 looks like. It's quite a tricky space. And the whole point is that these canonical forms are differential forms on this space. And the reason I've removed this point is precisely because it has a pole there. Okay, good. So there's something called, oh no, I've slowed right down. There's something called the tropical Torelli map, which is defined on the full moduli space mg trop, but I only care about its restriction to this open locus, tropical Torelli, to PG mod GLGZ. And what it does is, to a graph, it assigns the equivalence class of the symmetric matrix LG. Right. So this space is very closely related to Cullen-Volkmann's outer space, quotient by out FG. Anyway. So a famous theorem by Borel in the 70s showed that the stable cohomology of these spaces, so if I take the cohomology of PG mod GLGZ, let's say with real coefficients, is isomorphic to precisely this algebra omega can as an abstract graded exterior algebra. And it's spanned by what are called the Borel classes, which are the classes of trace x inverse dx, 4k plus 1. Cohomology classes. So what does this mean? So how do we interpret these canonical integrals? Well, they're sort of, they're gone. These things here. There are two ways to think about it. One is that you take these sort of God-given invariant forms here. They're the only ones which are stable. And you pull them back to this space and you integrate and you take the volume of a cell. Another way to say it is that if you're more interested in symmetric spaces, this symmetric space actually has a cellular decomposition, which goes back to Voronoi. And it's a sort of union of polyhedra. And some of these polyhedra are precisely the images of cells along the tropical Torelli map, and they're called graphical cells. So you can also think of a canonical integral as being the volume in this space of a graphical cell. So a canonical integral is, if you like, the volume, either volume of a cell on the moduli space or the volume of a graphical cell in, if you're more mathematically minded, you might prefer to sit on this space on the right. So not all the cells are graphical, there are other ones. I don't know what their volumes are. Right, so examples. So for me, it's a kind of a surprise that you have this quite natural mathematical question, and it automatically produces Feynman integrals out of thin air. Let me write here. Okay, so now examples. I'm going to try and catch up a bit. And then I'd like to talk about momenta, particle masses and momenta. So examples, the first example is the wheel with 3 spokes. And in this case, it turns out that when you compute the canonical integral omega 5 on the wheel with 3 spokes, it is literally 10 times the Feynman integral. And so in this, and only in this case, the canonical integrals and Feynman integrals coincide on the nose. So the canonical integral for the wheel of 3 spokes is 60 zeta of 3. Now, the next interesting graph is a wheel with 5 spokes, and we can consider omega 9. And with the help of a computer, you can check that this is 18 times the Feynman differential form, but there's a correction term, which is the product of the alphas, where you only look at the internal spokes of your wheels. There are 5 of them. And here you have psi W5 cubed omega. And what happens here, so this turns out to, the integral is zeta of 5. And what happens here is rather interesting because if you remember, for the residue, well, this integral actually gives a zeta of 7. It gives a completely different zeta value. But this integral precisely gives a linear combination of zeta 5 and zeta 7. And the linear combination is such that the zeta 7 precisely drops out, and you get a zeta value of a different weight appearing for the same graph. So recently with Oliver Schnett, so this is a theorem in progress, we computed these canonical integrals for all the wheels. It's actually very difficult. And we showed that it's some Catalan number. So this is a work in progress. But again, I warn, this is not at all the same as this results. For the residue, they're completely different wheels. They're wheels with odd spokes. The numbers are completely different weights. So this is literally the Borel regulator. I don't want to talk about this too much now because a few weeks ago I was standing exactly here giving a talk on precisely this topic. So there's a video of me a few weeks ago talking about exactly that in this very room, so I don't want to repeat myself. But this is the Borel regulator on K for n plus 1 Z. Again, I find it surprising that it's a Feynman integral. And there are lots of consequences of this. It gives new cohomology classes in various spaces. Should be a central binomial coefficient. That's what I mean. Oh, yes. Okay. It's a central binomial coefficient. Right, so that theorem has some mathematical consequences, which I won't discuss. Finally, I want to just give one more example. It's pretty much the only example that's one of the very few examples that's been computed so far. And it's the complete graph K5. So if we take the complete graph K5, which I don't know if I can draw it, but basically everything is connected to everything. Something like that. 1, 2, 3, 4, 5. Then you can compute the canonical integral K5 of the form Umgalt 5 wedge Umgalt 9. So this was done by Schnetz and Berinsky last year. And they showed that it gives a certain explicit multiple of zeta 3 times zeta 5 plus a certain explicit multiple of zeta 3, 5 minus 29 over 12 zeta of 8. So this combination, tantalizingly, is exactly the same combination that occurred in the residue, but for a completely different graph. And we don't really understand why. No, they're not, because in the single-bodied world, zeta 3, 5 is just zeta 3 times zeta 5. So the first interesting single-bodied ones in triple depth. And weight 11. There was, yes, hello. Yeah, I thought it looked simple. Thank you. K6, yeah. It looks surprisingly simple. Okay, so thank you very much, Eric. So let me try to do this. All right, that looks a lot more impressive now. Yeah, of course, of course. Thank you very much, Eric. So I don't know if I have time. Quick remark. This is interesting because there's a famous result by Minkowski going back over 100 years that this particular form actually computes the volume of a fundamental domain of P5 modulo GL5Z. Sort of modulo some scale action, but we don't care about that. So it really gives the volume of the fundamental domain of GL5Z. And so it's known by Minkowski that this is proportional to zeta 3 times zeta 5. And what's going on here is that if you look at GL5, it has this Voronoi decomposition I mentioned, and it essentially has three cells that sort of tessellate it. One of them is the cell associated to this graph via the tropical trolley map, but there are two others. And so what must be happening is that these two other cells are going to produce terms that sort of annihilate these other multiple zetas, and to produce a zeta 3 times zeta 5 in the end. But already this calculation tells you that the tropical trolley map is not surjective, for example. This fundamental domain cannot reduce to this single cell because of this zeta 3, 5 obstruction. So anyway, there's a whole story beginning with that, and I've given lots of lectures online. If you're interested in learning more, I invite you to look at them. If, however, you're not interested in that, then you're in luck, because I'm now going to slightly change topic, because I want to talk about particle masses and momenta in the remaining 10 minutes. So now we go back to I'm going to have to be a little bit hasty. So now we go back to graphs such as the one I had at the beginning with, something like this, but with incoming momenta. So I'm going to allow Qi in R2 or 4, and I'm going to allow particle masses. So these are all now allowed. I'm doing the full, and I want to see, is it the case that we can interpret real-world Feynman integrals such as those calculated every day for collider experiments? Do they also have this kind of mathematical interpretation, or do some of them have some? And the answer is yes. So what I'm going to do in d equals 2, I'm going to identify r squared with c. I'm going to choose some square root of -1. And in 4 space-time dimensions, I'm going to identify R4 with the ring of quaternions, which is R plus IR plus JR plus KR. Now, what does a general Feynman integral look like? In full generality, it's again an integral over this, this positive region of our favorite projective form, some arbitrary numerator, which can be exceptionally complicated, some power of the graph polynomial, but there's also a new player, which is what's sometimes called the second Szymanczyk polynomial. I give you quickly the definition. It depends on the masses and momenta, and it is a polynomial phi, which only depends on the particle momenta, plus this term involving the squares of the masses, is the sum of all edges, times psi g. So here I'm in Euclidean space, and phi g q is the sum over all spanning forests with two connected components. So these are often called two trees, the spanning two trees. And then you take the product, sorry, no, you don't. You take minus the total momentum flowing through the first tree, Euclidean dot product with the momentum flowing through the second tree, times the product of all edges not in the tree. And that gives you some other polynomial that's also very nice, but depends in a non-trivial way on the kinematics, the external momentum. Right, so now what I would like is a Laplacian, a kind of graph Laplacian whose determinant is going to give me this polynomial psi. And as far as I know, there isn't one off the shelf with the right properties. I mean, one can sort of cook things up, but there's one particularly nice one that's exactly the right size. So this is what I call the generalized Laplacian. And to define it, we choose what's called a momentum routing. But in the end, nothing will depend on this choice. So momentum routing is sort of getting this external momentum to flow through the graph. So for every edge E, it will be the data of either a complex number or a quaternion, depending whether we're in 2 or 4 dimensions, for all internal edges. And the requirement is that momentum is conserved at every vertex. Instead of saying that, let me just draw a vertex. A vertex will have some internal edges, which we're going to orient. And it's going to have some external half edges. So let's say this is Q1, Q2, and we just choose Q3. We're going to choose these internal momenta so that momentum is conserved. So this is very familiar. There's no unique way to choose them, but there exists always such a choice. So armed with this, we do something very similar. I define a generalized incidence matrix, H tilde G, same as before. I just take the incidence matrix HG we had before, and I add an extra column. And in that column, I put all the momentum routings, all the choices of momentum for each edge. So I've just extended it by 1. And to encode the masses, I have a matrix that's exactly the same dimensions, which is just a 0 matrix. And I have the masses of each edge in the final column. And then we can define a generalized graph Laplacian. Lambda tilde G to be the conjugate transpose dg hg plus m tilde g transpose gg mg. So this is the conjugate transpose. It's complex conjugate or quaternionic conjugate, depending on which setting we're in. And so this matrix lambda tilde is a complex Hermitian or a quaternionic Hermitian matrix, depending on whether in two or four dimensions. And it has dimension, it's rank Hg plus 1. It's exactly one more usual graph Laplacian. And so the theorem is that in the complex case, the determinant of this generalized Laplacian is the second semantic polynomial. And in the other case, we take the quaternionic determinant, which I write with a capital G. It's the square of the second semantic polynomial, in the case d equals 4. Right. I was going to give an example, but I'm out of time. So anyway, the upshot is that we can define more canonical forms. They're new canonical forms. For example, we can take what I call omega overline G, 2k plus 1. As before, it's just the trace, but now of this generalized Laplacian. So this is in the case d equals 2. And what's interesting here is that this generalized Laplacian is no longer symmetric. So now we have more canonical forms to play with. There's one for every odd number bigger than 1. And we have a quaternionic version. In the quaternionic case, that's not true. We only have, for some strange reason, we have to take the quaternionic trace. Again, in the quaternionic case, half of them vanish. And I was going to write it, but I'm out of time. These classes precisely correspond to the stable cohomology of GLN C and of GLN in the quaternions. So these were computed by Henri Cartan, I think, who computed these invariant forms a long time ago. So there's a one-to-one correspondence between these forms and the stable cohomology of these general linear groups. I'm out of time, so let me just say theorem. Oh, I don't want to do that. So the theorem is that you can write down the integrals in the same way, and they always converge. So theorem. So we can define canonical. You take any wedge product of these forms you like, and you can integrate them over any graph, and you get canonical integrals, which now depend on masses and momenta. They're always finite. They have lots of amazing properties such as functional equations and Stokes formula and so on. And they are of the form, this. So they are a particular class, they pick out a particular class of bona fide Feynman integrals with special properties. So I'll stop there. I'm sorry for running over by a minute.
Thank you very much. Excellent. So we actually have some extra time today because we have a long lunch. It's okay that we're a little bit over time, so we have time for some questions. So Ollie.
Hi, how do the differential equations of these mass and momentum dependent integrals typically look like, say, in comparison with the differential equations we find in the Feynman integral literature?
So you mean differential equations with respect to kinematics?
Absolutely, yeah.
It's an excellent question. I haven't looked yet.
Thanks.
Very good question. I think, yeah, very good question.
A rather naive question. If you wanted to do this in 6 dimensions, you were wedded to having complex numbers and quaternions.
Yes.
Would there be a straightforward way to do this?
Straightforward. No, but there are things which generalize the quaternions, which have been cooked up to express momenta and in higher dimensional spaces that are not very efficient. The ranks go up very big, very quickly. I think I may have tried 1 or 2, but what happens is that when you try these, what can go wrong is that these forms can end up vanishing for symmetry reasons. So I suspect that it's not going to give very much, but I'm not completely sure.
Yes, in the case of the real for the vacuum diagram, the only parameter of the matrix you had were the Schwinger parameters. So I understand that you integrate them all. In that case, it seems that, I mean, your matrix, symmetric matrix or Hermitian matrix depend on masses and external momenta.
Yes.
So what does happen about the integral?
I don't integrate them. I'm only integrating. So when you're right. So yeah, it was a bit fast. So here, this lambda tilde g. Let me just take the opportunity to show you what it looks like. So if I have this graph with a momentum, in fact, it always has this general shape. It has a very simple shape. It has the ordinary graph Laplacian in one block. It has this block diagonal shape, and here it has certain linear forms in the alphas and the mu's, and here they're complex conjugates. And all the mass dependencies here in a very simple way. It's something like me squared plus mu e bar alpha e. So all the mass is here. So when you look at this matrix, it's a matrix in the alphas, the mu's, and the m's, as you rightly point out. But when you take the derivative, the d, you only differentiate with respect to the alphas, and you keep the mu's and the m's constant. And so when you take this matrix and you take the wedge product, you know, the only differentials are the alphas.
Is it like a real cycle in the space of Hermitian matrix?
Yeah, so the image, yeah, well, so this is a differential form. This is a bi-invariant differential form in the space of Hermitian matrices. And what happens is that this region here, mapped to the space of matrices via this map, produces a region in the space of Hermitian matrices. It produces a certain polytope in the space of Hermitian matrices. So it's the map sort of alpha I. So I've made a mess of this board. You know, alpha 1 up to alpha E, G, mapped to this matrix, which depends on the alphas, is a map from this simplex, this, you know, simplex into, and it maps to a complicated polytope in the space of Hermitian matrices. And we're integrating over that.
Okay, thank you.
Yeah, I was wondering if there is any interest in considering tropicalization of this type of integrals, where we replace this polynomials by their tropical limit, and would expect to get some rational numbers.
That's I don't know. That's a great question. I'd like to say that these are already a tropicalization in some sense. Yeah. So in fact, the way I derived this lambda tilde g was by looking at, so if you have a Riemann surface, you can look at the Riemann polarization form, which is omega. If you take a basis of holomorphic 1 forms, and you can integrate the holomorphic forms, that gives you a Hermitian matrix. This is the Riemann polarization form, essentially. This is the graph Laplacian. If you tropicalize this, you get the graph Laplacian. You can do this with punctures. Now you have to be careful about what this means, because they're not necessarily smooth integrals. But you can, when you do a tropical version of that, you get exactly this matrix. And so this is the tropicalization of something that's much more stringy. So I thought you were going to ask, but you can tropical. Yeah, that's interesting as well. I have no idea. You have to ask Eric about that.
Well, okay, so we have a question from Pierre in the back. Next.
Yes. So, when you look at this graph with external momenta,
yes,
it's very important to impose the physical condition for the momentum conservation.
Yes.
In particular, in 4 dimension, there's the gram determinant condition.
Yes.
So if I take, for example, the penta box or the double box with 6 legs,
yes,
you only see that the Hodge structure is rank 2. That means there's an elliptic curve only after you impose the gram determinant.
Yes.
So how do you impose that in your?
I used it. I had to when I did the momentum routing only exists because I've got momentum conservation.
No, but the gram determinant is an extra condition. It's something.
So you're saying you want
an
an extra condition over and above momentum.
Yes, it's a quadratic condition because, for example, if you have 6 momenta in 4 dimensions.
Yeah, sure. So if you have they're related, of course. So but I fixed the dimension of space-time. So that's somehow intrinsic it's true. So if I take a d equals 2 and I have a graph with 15 external legs, clearly there's some complicated algebraic relations, collinearity relations between external momentum, because if I take 3 vectors in 2-dimensional space, they're linearly related. And but that's hardwired in because I'm constrained in relation to his question, right? I think I'm constrained to being in 2 and 4 dimensions.
Right, but I don't think that's enough. I mean, you should. Okay.
So if I were to drop that condition,
maybe you should do that.
Then again, back to Hugh's question, then I have to cook up some way of encoding momenta in some kind of jazzed up quaternion algebra. So there's these sort of sesquiu.
Yeah, but that's precisely the point. I mean, the gram determinant has to do with some jump in the rank of the Hodge structure, and you really see, for example, the elliptic nerve.
Absolutely, the weight drops. No, I totally agree.
On some graph, only after you have imposed that.
I totally agree. But that condition is imposed, and I think it's the weight condition you're talking about. This Borel class. So I'm not sure if this has been fully worked out, but this Borel class. This is just sort of C infinity. This is C infinity cohomology, but you can give it a Hodge structure.
Okay.
And these Borel classes have a certain weight. They correspond to a certain Tate motive. It's going to produce the Hodge class in exactly the weight you're saying.
Okay.
And the only reason it works is because we've so for this massive box diagram, I didn't have time to talk about it. If I compute the canonical integral associated to omega 3, then it produces a dilogarithm. It's exactly the Feynman.
This one is, I mean, I'm saying, for example, take the double box with 6 legs.
I haven't tried that. I've no idea.
And then you see that indeed, if you don't impose the gram determinant condition, you have a Hodge structure that is higher rank, and then you have the rank jump exactly on the locus of the.
That makes perfect sense.
And so that.
But in that case, that makes it plausible that if you impose the gram condition, then it may be that the Feynman integral is one of these canonical guys, which has to be in that lower weight.
Okay, that's a good point. Thank you.
So I happen to know that we have one question on Zoom as well from Marcus Barry.
Oh.
So you can unmute yourself and ask the question, Marcus.
Can you hear me?
Well, I will try this. So try again.
Can you hear me?
Yes.
Hi, Francis. Thank you very much for this talk. I have a much more basic question than the previous ones. How should I think of the length on these metric graphs? Because I think of the Schwinger parameter alpha as kind of a length. But what is the length L? What does it mean sort of physically, or can you characterize it more, please?
Yeah, so the quick answer is that L, oh, sorry, that's my voice. The quick answer is that L is alpha. I just switched notations. But I like to think of alpha E as a coordinate on an algebraic variety. So it's like a, it's a coordinate, whereas LE is the real number, which is the length of that particular edge. But alpha is L. So they're the same thing. You can think of them as the same thing.
Even the same letter of the rotation.
Depending on your handwriting.
Okay, thank you very much.
Thank
Okay,
you.
final question from Don.
Just since you ran out of time, you didn't give any example of the things when there are momentum and wet masses and so on. Can you at least say what kind of functions you get? And before they were just numbers, multiple functions. Are these polylogarithms?
Yeah, so well, absolutely. Yes, as you know, if we take,
only polylogarithms.
I don't know, that's a great question. So if we integrate a Borel regulator over some polytope, we expect to get polylogs. And the only case that I've done so far is this one, which I scribbled. So if we take this, so here D is 2 dimensions, I think. So I take this Feynman diagram, Q1, Q2, Q3, Q4. So here the momenta are in, are in complex numbers. And then I allow masses. I don't know where I put the masses, it's just anywhere, M1, M2. So this is a very complicated Feynman integral to compute. It's not easy. But what I do is I can compute the simplest possible a canonical differential form is this cohomology class here. So this would be K3. This is a K3, right? So omega 3 of G. And this turns out to be some rather beautiful function, a symmetric function of the masses momenta, which I can give you if you're interested. Omega G over psi G QM squared, I believe. Yes, I think that's right. And therefore, the canonical integral of this graph is exactly the Feynman integral, which is known in the literature. And it's known that this is something like a sum of 20 or so dilogarithms, very complicated dilogarithms in the Q's and the M's with a very complicated, with sort of square roots and things in the arguments. But just one final comment, because I think it may interest you, is that there's a Stokes formula which comes from this theory, which I didn't have time to mention, which essentially when the degrees are correct and in a very simple case, gives you relations like this. You look at the canonical integrals where you contract over every edge and it gives 0. And we can apply this Stokes formula to the pentagon, 1, 2, 3, 4, 5. And what this gives is 0. And if I take a pentagon and I contract an edge, say this one, then clearly what we get is a graph like this, and this double line means that we just take the sum of the 2 incoming momenta. And so what we get here is a 5-term relation, which is the sum of the canonical integrals of 5 different box diagrams, which is the same as the ordinary Feynman integrals with this prefactor, just by pure thought. And so that should be the 5-term functional equation of the dilogarithm. But bearing in mind that this thing is a combination of about, I don't know, a horrible number of dilogarithms. So yes, this is an excellent question. It'd be wonderful to know if they're always polylogarithms. I just don't know.
Okay, excellent. So let's thank Francis again. So we're going to start right away with the next talk by Guillaume. We're just going to set up the slides and everything.
Is that more the product you're looking for? Sorry, it's showing my metal off, that's all.
Guillaume, are you already set up your thing, right?
Yeah, we're all good. Man. We're all good. All good.